So, our keynote speaker, the culmination of the conference. I recently had the pleasure of hearing Rebecca Goldstein, who was our 2011 Humanist of the Year, give a philosophy lecture on the will to matter. She was essentially arguing that the craving that we humans feel to matter to each other drives the way we satisfy our need for meaning. Of course, the way my literal mind works, I could not help but juxtapose her meaning of the word matter with the one that my inner physicist hears, that matter is the stuff of our universe, the stuff of our existence. It is the study of matter and the forces which act on it that is the lifeblood of physics. But some physicists take that study one step farther to look at the milieu in which matter matters. Sean Carroll, a theoretical physicist at Caltech in Pasadena, California, just up the road, and most recently the author of The Particle at the End of the Universe, How the Higgs Boson Leads Us to the Edge of a New World, does exactly that. He has published on topics as seemingly diverse as particle physics, gravitation, the arrow of time, cosmology. But of course, all of these are related at the fundamental level when we think about them as different ways of understanding matter and how matter interacts. So bringing this around to the initial juxtaposition between matter and mattering, I find myself wondering if my relevance to other people is enough to satisfy my need for meaning, and I don't think it is. Part of why I studied physics in the first place is that I also craved knowledge about what drives the universe around me, how matter itself matters. Today, we have the great privilege of hearing from Dr. Carroll, who I hear is a wonderfully dynamic speaker, on what meaning a rational person can derive from the impersonal universe around us, how to figure out what matters about matter. So, before I make that final introduction, I want to remind everyone we are being live streamed. So if you have friends around the world you want to share this with, conference.americanhumanist.org. Now, I give you Dr. Sean M. Carroll. Thank you.
Thank you very much. Thanks, everyone. I'm hoping the slides are going to appear here soon. Oh, yes, look, there we go. So it's a great pleasure, a great honor to be here as the keynote speaker. It was a little bit of a surprise to get the invitation. My first reaction in these situations is because, you know, I have an evil twin. There's a Sean Carroll who's a biologist. So I need to say, are you sure you have the right Sean Carroll? And oftentimes they're embarrassed and they go, all right, you can come. But I've actually been disinvited from other conferences, so it's very, very nice to be here to be talking about purpose and the universe. And it's not purpose of the universe. I want to be very, nuanced and as subtle as I can be about how these two things connect. I'm a scientist, a cosmologist, a theoretical physicist. We're here at the American Humanist organization. I want to connect what it means to be a human being to how the universe behaves and how the universe acts. And I want to start by telling you a depressing story. Lucia de Burke, you may have heard this story before. She was a Dutch nurse who in 2004 was convicted for life imprisonment. She was found guilty of murdering 7 infant children and the attempted murder of 3 more, which would have made her the largest serial killer in the history of the Netherlands. One of the most important pieces of evidence against her was math. In particular, a statistical calculation that asked, how likely is it that a single nurse would have been on duty when these different children died in the hospital? And the answer from the expert witness was there was only a 1 in 342 million chance that that would have happened. Now, this got a lot of play in the science, math, geek community because that was not right. That was not the right way to calculate the probabilities. When real experts chimed in, they said, in fact, the probability is 1 in 26, which is rather different than 1 in 300 million. Since that was the strongest evidence against her in 2010, she was exonerated by another trial. And so the math enthusiasts proclaimed that we all need to understand math better. The point I want to make is a little bit different. It's true, we all do need to understand math better. I'm in favor of that. But why were we so easily seduced by the bad math? This image that you see right here is a sketch that was done during the trial, reprinted in newspapers in the Netherlands. Here's an actual photograph of Lucia de Burgh, and of course, photographs can be just as dishonest as sketches, but the claim I want to make is that the people behind the prosecution and the public opinion behind those following the trial was seduced by the idea that we always want to find something to blame. We want to find a reason why things happen. We don't want to accept that children die in children's hospitals. Very sick children sometimes just die, and there's not anyone who caused it to happen. The fundamental laws of physics, you might say, caused it to happen, but there's no person on which we can put the blame. And the desire to put the blame on someone was a big part of why this nurse was so readily convicted. And you find this, this kind of reasoning over and over again. Famously, Pat Robertson, the evangelical Christian, after the earthquake devastated Haiti, he told a little story. And you know the story is true because he says it's a true story. And that's, you know, well then. And the story is that the Haitians made a pact with the devil to get their quote-unquote freedom from the French colonialists. And ever since then, the devil has been punishing them for wanting to be free by visiting various sorts of terrible things on their community. Every time there's a terrible disaster, whether it's a terrorist attack or a natural disaster, an earthquake, a tornado, a tsunami, a hurricane, people want to blame somebody. People want to find a reason why it was like that and say that it didn't have to be that way. If you were more virtuous, it wouldn't have occurred like that. And it's not just evangelical preachers. This kind of thinking goes back at least as far, much further, but you know, famously in a celebrated set of works by the philosophers, Baruch Spinoza, Gottfried Wilhelm Leibniz, they invented something called the principle of sufficient reason. Basically, it's just a statement that whenever anything happens, there's a reason why it happened. Nothing happens without a reason. Every event, every occurrence, every thing that we see in the universe can be blamed or credited to something else happening. And one of the two primary points I want to make in the talk is that this is just nonsense. That sometimes things just happen. They happen in accordance with the laws of nature, but not for what any person would accept as a reason or a cause over and above the fact that that's what happens next according to the laws of physics. So the idea that I want to put on the table, the ethos that I think that all good scientifically minded humanist people should accept, is that we do not get to place demands on the universe. We do not get to decide ahead of time by pure thought how the universe works. Whether or not you like the way the universe works is completely irrelevant to what the universe does. Our job as empiricists is to say we should consider every possible way the universe could possibly behave. Maybe there are causes, maybe there are not, maybe there's someone to blame, maybe it's random, maybe it's deterministic, and then we should go out and do the experiments. We should figure out which of the infinite number of hypotheses we're allowed to come up with is the best explanation for the data, and then we should accept it. And that acceptance often requires a great amount of courage. Sometimes what the universe does doesn't fit with what we want it to do. So let's tease out a little bit of the history of this tension between finding reasons for things, demanding that the universe has a purpose, versus just accepting the way the universe actually is. So one way that things can have a purpose, obviously, is if they were designed to have a purpose. A Roomba has a purpose, right? A Roomba, the little things, the robots that vacuum your room, it was made to vacuum your room, right? There's a designer for the Roomba. It has a purpose. That's perfectly okay. Can we extend that kind of reasoning to the entire universe? Is there a person, a conscious being, that designed the universe in a certain way? Plato thought there was, and I need to apologize. I'm only trying to apologize once. Consider this a blanket apology for all of the terrible damage I'm going to do to many, many subtle thinkers by quoting them in one little sentence and summing up their thinking this way. There's a lot more behind this. The philosophers and historians will have to forgive me. But Plato does have this tradition of saying that there are reasons why things happen in the universe. Everything that comes into existence must have done so because something caused it to come into existence. Of course, this has been adopted by Christianity, by many different modern religious traditions. So the Baltimore Catechism, which is what was taught in American Catholic high schools for many, many years, explains what the purpose of us being here is. It's because God made us to show forth his goodness. And if you want a slightly more modern version of that, Rick Warren, the evangelical preacher who wrote The Purpose-Driven Life, which sold about a gazillion copies, if you want the technical scientific term. The Purpose-Driven Life has my favorite opening line of any book ever, except for Pride and Prejudice. But the opening line is, "It's not about you." And this startled me when I read it because it's basically a self-help book, right? The Purpose-Driven Life is a little guidebook. It even has like checklists day by day, what you should do to become a better person. You would expect, or I would have expected before opening it, that it's going to flatter you. It's going to tell you nice things about yourself. His first sentence is that it's not about you. Of course, then the subtext is it's about God, and you're supposed to devote yourself to God, and the whole purpose-drivenness of the book is to find the purpose that God has for you. But I mention this mostly because even without God, there can still be purposes. There can be apersonal purposes. There can be what we would call teleology. There can be inherent or transcendental purposes to the material, the stuff out of which the universe is made. Aristotle used this kind of language, insert apology for being brutal here, but he was wonderfully systematic, Aristotle, right? He wrote down all the different kinds of causes and purposes there could be, and he explained physics in terms of causes. Why does Earth tend to go down and fire tend to go up? Because Earth wants to be closer to the Earth, fire wants to be closer to the heavens. It's teleological in the sense that you explain the dynamics, the evolution right in front of you in terms of a future goal. You say, why does the Earth fall down? Why does a stone fall? Not because there's something called gravity that pulls it, and according to some equations, but because the stone's natural place to be is closer to the ground, therefore it tries to get there. That's teleology, explaining current motivations, current actions in terms of a future goal. Teilhard de Chardin invented a very elaborate version of this called the omega point theory, which has been adopted by some physics colleague crackpots of mine as a way of thinking about the entire evolution of the universe toward greater complexity, consciousness, and so forth. And sometimes this idea of future teleology has been given a modern pseudoscientific spin. Hubert Spencer is the person who is most identified with the phrase social Darwinism. I don't know if he ever used that phrase, but he put forward these ideas that evolution is a mechanism of progress, that it's not simply the mindless motion of genes back and forth in a difficult and competitive environment, but that evolution is a means by which the universe naturally and inevitably moves towards greater progress, greater complexity, greater goodness. He applied it to sociology as well as to biology. So there's this long tradition of the temptation to see purpose, to see teleology in the workings of nature. There is also the counter-tradition. You don't need to wait until the 20th century to find the response to this. There are ancient thinkers who rejected the idea of teleology and purpose. Democritus, the founder of the idea that we are made of atoms, one of the great early particle physicists, he didn't write a lot, or his writings were not preserved, but we find in Aristotle arguments against Democritus. And Aristotle is complaining here because Democritus thinks that things just happen. Things just happen over and over again because there are these laws, these necessities, these patterns that are inviolable and are always going to explain what happens next. He is ignoring the final causes that Aristotle likes to think are there. Lucretius, a Roman poet who followed in the tradition of Epicurus and Democritus, invented a whole cosmology based on this. And he actually applied this to the creation of the universe out of nothingness. He said, you know, the atoms are just bumping into each other. They don't have any plans. They don't have any purposes. They don't have any future goals. They're just randomly bumping into each other. But if they shuffle and jumble in many ways and you wait long enough, at last the atoms will fall into such an arrangement as will create this universe. The universe, Lucretius says, just one of those things that happens from time to time. What these guys don't have, these guys are on the right track from our modern point of view. What they don't have, equations. And I know you've been very patient. You want to see the equations. Here you go. There will be homework. So There might be 2 or 3 of you in the audience, you know, the kids among you who haven't learned differential calculus yet, so that's okay. I put the equations up here. You know why I put the equations up here? Because they're pretty. The equations are very, very beautiful, the equations of modern physics, and this won't be the last one. Here is Isaac Newton, who really put the laws of physics down in something that is at least recognizable to our modern eyes. And what he says is the following: you tell me what the universe is doing right now, that is to say the position and the motion of every little particle out of which stuff is made, I will tell you what it's going to do next. And what that means in equations is that the laws of physics are differential equations in time. What does that mean? That just means that the current state of the universe determines its future evolution into the immediate future, and then you do calculus on it and you can build up the entire future history, or for that matter, the entire past history. And you might say, and you indicate this in the equations by this d by dt is acting on something. So x is the position. D by dt says, how is the position changing? Well, we call that the velocity. How is the velocity changing? Well, we call that the force. And this paradigm has remained absolutely constant for all of physics since Isaac Newton, whether it's Maxwell with electromagnetism, Einstein with relativity, whether it's Erwin Schrödinger with quantum mechanics. Look at Schrödinger's equation. It looks the same. You have a wave function for the universe. Its time derivative is given by something on the right-hand side. How it evolves forward in time. Superstring theory, the standard model of particle physics, all modern physics works in this way. It is not teleological. It is instantaneous. You give me the universe now, I will give it to you in the future. And this implication of Newton's discovery was actually not spelled out by Newton, but by Pierre-Simon Laplace. You might know Laplace as the mathematician and physicist who tweaked Napoleon's nose. Napoleon says, how come I don't find God in your book about the motions of the planets? And Laplace says, well, I had no need of that hypothesis, which is kind of remarkable because Laplace was mostly a social climber. He managed to leave Paris and come back exactly in tune with when they were having revolutions and killing nobles like himself. And somehow he lost his cool in front of Napoleon, but he survived and flourished. And what he says, among many other things that Laplace figured out, is an implication of Newton's laws of physics. The implication is the following: if you were a sufficiently vast intellect, he refers to a vast intellect. Later, more colorful writers called this intellect Laplace's demon, but as a non-religious person, he didn't call it a demon. He said an intellect who knew everything about the current state of the universe, every position, every particle, everything that makes up the universe right now, and perfect knowledge of the laws of physics, and perfect calculational ability. You would know everything there is to know about the future of the universe and everything that had happened in the past. Nothing would be uncertain. The future, just like the past, would be present before its eyes. This is counterintuitive to us. We think that the past is different from the future in some way. The past happened, after all. Future hasn't happened yet. I can make choices about the future. I cannot make choices about the past. Laplace says if you take the fundamental laws of physics seriously, you're wrong. That every moment in the history of the universe is contained in every other moment. If you want pictures, if you're that right brain kind of person, here's different kinds of theories you might imagine, possibly, hypothetically, describe how the world works. There could be a historical theory. As the universe marches upward in time, to predict the future, you might need to know everything that happened in the past. That's possible. If you were more Aristotelian, teleological, what you would say is, you tell me the current state of the universe and the future goal, where the universe wants to go to, and then I will tell you how the universe gets there. That's how physics would work. What Laplace says is really radically different. He says, you give me the universe right now, or at any other one moment of time, and there's something called conservation of information. The information you know to predict the future or retrodict the past is the same at every moment in time. This one moment is enough to determine everything else that happens in the history of the universe. Now you might say, well, yes, but Laplace was talking about Newtonian mechanics. We know better now. Let's talk a little bit about what we know now, how modern physics works. Because not only is it similar to this Laplacian paradigm, but there's actually much stronger implications about what we know from modern physics. So here is fundamental particle physics, circa 1935. You could have forgiven the 1930s era physicists for being a little bit optimistic. I'm not actually sure that there are any embarrassing quotes from 1930s era physicists, but they were in a position at the time when they had discovered enough elementary particles to make sense of every experiment they knew about. There were atoms. They knew that atoms had electrons on the outskirts and a nucleus inside. They knew that the nuclei were made of neutrons and protons stuck together. So there's three basic particles, electrons, neutrons, protons. And that's enough to make up everything that you see around you. You, me, the table, the 1930s physicists, etc. They were interacting with three forces. There's an electromagnetic force that held the electrons to the protons, a nuclear force that held the neutrons and protons together in the nucleus, and gravity that just pulls everything into everything else. Sometimes the course of scientific progress takes our pre-existing understanding and throws it away, but very often the course of scientific progress builds on what we know. This idea of how atoms work is still true now and still will be true a million years in the future. But we've improved it a little bit. So here's fundamental physics today. Still neutrons and protons and electrons, but we've figured out that the neutrons and protons are made of quarks. It only takes two different kinds of quarks to make neutrons and protons, ups and downs. Two ups and a down in a proton, two downs and an up in a neutron. We do have one more particle, the neutrino, which is created, for instance, in the sun. When the sun is shining, when two protons come together in the nuclear fusion in the sun, one of those protons turns into a neutron and spits out a neutrino, a light neutral particle. And that interaction is by a new force of nature called the weak nuclear force. It's the strong nuclear force that holds the particles together in the nucleus. The weak nuclear force creates neutrinos and helps the sun shine. Other than that, we still have gravity, we still have electromagnetism. It's the same basic pattern, but the pattern is repeated 3 times. We not only have an up quark and a down quark, we have a charm quark and a strange quark, a whole nother generation. It's like these are the baby quarks and there's the parent quarks. And there's also the top quark and the bottom quark. There's the grandfather and grandmother quarks. These 3 generations, nobody has any idea why the world is like that. When it was first discovered, the famous physicist I.I. Rabi said, "Who ordered that?" Nobody has answered Rabi's question correctly. It might be a little teleological presupposition in his question, but... And there's also, of course, something called the Higgs field in the background of everything. There's a whole lecture I could give you on the Higgs field. I'm not going to give it to you now, but I hear there's a really great book you can buy on Amazon that explains it all. It explains why symmetries are broken and why these particles have mass. But you see the basic picture is still intact. And what I want to go into a little bit is not the intricacies of how the different particles play out, but the explanatory closure of this theory that we have called the standard model of particle physics, supplemented with general relativity, because strictly speaking, gravity doesn't fit into particle physics, but we have a theory of gravity that works pretty well. So we have the standard model plus general relativity is not the final theory. Nobody in the world thinks that these are the ultimate, once and for all, finished laws of physics. But they are the right laws of physics in a certain regime. And that regime is pretty big, and we all live in it. So this theory is internally complete and coherent. There's nothing missing. There's nothing that it can't explain on its own terms. No experiment ever done here on Earth has contradicted this theory. And I say on Earth because there's still the sky. And the sky tells us about dark matter and dark energy and so forth. And those are not explained by the standard model of particle physics. They are also irrelevant to your everyday life unless your everyday life is being a particle physicist. And it's settled. We're done. In July 2012, we discovered the Higgs boson. That was the last particle in the standard model of particle physics. We could still discover more particles. That is absolutely necessary. That is absolutely allowed, but is not necessary by any logic that we currently have. There's no data. There's no theory. There is no experimental evidence that we need more particles than this to explain what we have already observed here in our laboratories. So what I'm saying here is that physics falls into different regimes. You don't need to know about dark matter to explain what happens when 2 protons come together to form nuclear fusion. In the regime of the everyday world, in the regime that you and I live and experience as we go through our day, this theory, the standard model plus general relativity, explains everything we have ever seen. And I know what you're saying. Where's the equation that shows me this? Here it is. There you go. This, in one equation, is the physics underlying the world that you have experienced, everything you've ever seen with your eyes, touched with your fingers, tasted with your tongue, heard with your ears, and so forth. I'm not going to explain everything, yet that's... Yes, you want me to explain it? All right. Here is quantum mechanics. There is space-time. There is gravity. Here are the other forces of nature. This stuff is matter. It's interesting. Electrons, quarks, neutrinos. And this is the Higgs boson. Love it as we do. And nowhere in here is there purpose, is there teleology, is there design. It's a pattern. It's an ironclad thing that the universe does. Here are the ingredients. March them forward using the laws of physics.
What's the equation name?
I don't know. Name it Sean's equation. I don't know what we... No one ever writes this equation down, but I did. So there you go. It's just we tend to write down the individual pieces one at a time. We think about relativity, we think about the Higgs boson, etc. I just added them all together to make one big equation. Now, what you really should be asking is not where are the equations, because here they are, but how do we know that there isn't new physics that is absolutely crucial to our everyday lives? You know, there's all sorts of claims in the historical literature of physicists overclaiming what they knew at the time. And so I'm trying to be very, very accurate about what we're allowed to claim and what we're not. And what we need to understand why we're confident that this is the everyday world is a little primer in quantum field theory. So I'm very glad that the Humanist Association has given me these 3 hours to give you a set of lectures on quantum field theory. Quantum field theory, it's a very funny thing. If you're a modern physicist, if you go to graduate school and you learn physics, quantum field theory is how nature works at the fundamental level according to the best theories we currently have. Every graduate student learns it. It's the centerpiece of what we do in modern physics. And we don't tell anybody. You can't buy popular books that explain the principles of quantum field theory. You can buy books about particle physics. You can buy books about relativity, quantum mechanics. My book's about wormholes and superstring theory and the multiverse, but how the world actually works, quantum field theory, we tend to be reluctant to explain it to you until now. So here you are. Quantum field theory is just one sentence. You know, we think about, well, it's two sentences. One is quantum mechanics, the other one is field theory. Quantum mechanics says that there's a very big difference between what you see when you look at the universe and what there actually is. What you see when you look at an electron is there's an electron at a location. When you're not looking at it, there's not an electron at a location. There's a wave function, a space of possibilities that gives the probability of seeing the electron in every possible different location. Field theory is actually, for this purpose, the more dramatic statement. It's that the universe is not made of particles at all. It's made of fields. If you had a little bit of physics education, you might have heard the argument between is light a particle or a wave. It's very unlikely that you heard the answer. It's a wave. The universe is made of waves. It is not made of particles. Waves are more important. Waves in fields are what the universe is fundamentally made of. Why are there particles at all? That's the quantum part. When you look at the waves, you see particles. What's happening when the light comes to your eyeballs is that there's an electromagnetic wave propagating out from the light bulb. When your eyeball sees it, it's in the form of individual flashes known as photons, particles, packets of energy. But that's not what fundamentally exists. What fundamentally exists is the electromagnetic field. It's only your perception of it that is in the form of these packets called particles. And that's not just true for photons, that's true for atoms, for electrons, for quarks. There's an electron field, there's an up quark field, there's a down quark field, and when we look, the vibrations in these fields are what we perceive as particles. What is the world made of? It's a set of fields, a set of numbers that fill space. What is the value of the electromagnetic field, the electron field, the gravitational field, and so forth? And quantum field theory applies quantum mechanics to this and tells you how the world works. So very roughly speaking, if you have a wave, if you have a field that fills the universe and it's jiggling, the height by which it jiggles, the amplitude, tells you how many particles you will see when you look at it, or the strength of the force you are experiencing. And the wavelength that you see tells you how far that force stretches or how heavy that particle is. There's a little translation dictionary between the field language and the particle language. And why is this important? So actually, I don't have the 3 hours. That was it. That was quantum field theory. Thanks. Why is this important? Because quantum field theory lets us quantify the scope of our understanding. It divides a line between what is accessible to us and what is inaccessible to us. And this was more or less figured out by this guy, Ken Wilson, a very, very foundational, crucial physicist of the 20th century whose name you haven't heard. You've heard of Stephen Hawking, Richard Feynman, and Albert Einstein. Ken Wilson told us how the world works. It's quantum field theory, and you organize quantum field theory by looking at different length scales. So what if there were new fields, new particles, if you looked at them? What if there were new fields we hadn't discovered yet? How would you know? Wilson tells you how you would know. Basically, you tell me how long the range of the field is, or how massive it is. And it goes, by the way, the longer the range is, the lower the mass is. And you tell me how strongly it interacts with everything else. So guess what? If the range is too short, you won't see it. Or if it's too weakly interacting, you won't notice it. We believe that dark matter particles are all around us. We believe that dark matter particles are coming through your body right now. And they're absolutely irrelevant. You can't blame dark matter for indigestion or nausea or anything like that, because the dark matter doesn't interact with you. It's too weakly interacting. So how do we know if there are new particles and new forces? Well, if they're up here, we would find them. If they're down here, we won't. If they're up here, they are the known knowns, in Donald Rumsfeld's formulation. If they're down here, they are the known unknowns. We know that we don't know what happens at very weak couplings or very short ranges. So where are the unknown unknowns? Only the statement that quantum field theory might not be right. It's possible. That was the ethos I already told you. I can't insist that quantum field theory is right. There's zero evidence, there's zero reason to believe that quantum field theory is right, but it's a possibility. That would be the unknown unknowns. So if this picture is right, if we think we can find things, if they're in the findable, accessible regime, how do we do it? So you might say, well, maybe there's a new particle. Maybe you think that conscious thought is just a matter of atoms and electromagnetism in your brain, but I think that I'm going to play by the scientific rules. Quantum field theory is right, but there's a new particle, the Zilbot particle. And this plays a crucial role in how you think. It gives consciousness to the human brain. All right, if that were true, what you're saying is that there are ordinary particles, protons, electrons, and so forth. There's the new particle, the Zilbot, and somehow it interacts. Somehow there's a little Feynman diagram that explains how this new particle you want to invent couples, interacts, talks to the particles we know and love. And there is a law in quantum field theory that says I can take this diagram that tells you how the proton and the Zilbot interact with each other, and I can rotate it by 90 degrees, and I predict a new phenomenon. What I predict is that two protons can smash together and make Zilbots. And we've done that. We love smashing protons together. That's what really gets particle physicists excited. We spend billions of dollars building accelerators underneath Chicago and Geneva, smashing protons together and watching what comes out. And what comes out are not Zilbots. There are no particles that have ever been discovered in particle accelerators that would interact strongly enough with the atoms in your brain to have any effect on consciousness, on biology, on life here on Earth in any way whatsoever. As far as you and I and our lives are concerned, physics is complete. We know the underlying physics that is relevant to everyday life. If we didn't, we would find it very, very quickly. So I'm just going to emphasize this because I've said this before in other audiences. There are always people who don't quite accept what I'm saying here, so I'm going to combat that by saying it again. Could new particles hide from our view? Yes. They can. There could be new particles out there. There are new particles out there. We don't know what the dark matter is, for example, but we know how new particles could hide from our view. If they're either very weakly interacting, too heavy to be created, or too short-lived to detect. That's how they can hide. And if they hide that way, they're not lurking in your brain. They wouldn't interact, they wouldn't be made, they wouldn't live long enough. If we can't find them, then they're not relevant to you, me, and this warm, noisy regime in which we biologically find ourselves. Could there be new forces? Of course there could be new forces. There could be new forces if they interact very, very weakly, if they only stretch over very, very short ranges. We're looking for them. Here's an experiment at the University of Washington, looking for new forces of nature. We are not closed-minded about this. We want to find new forces of nature, but we've put limits on what they can be. And the limits are good enough to say they're not relevant for you, me, in our everyday lives. I know that some of you don't like equations, but what you really love are data plots. So here is the data. Experimental constraints on new forces of nature that we haven't found yet. The range, remember the plot that I showed you inspired by Ken Wilson, how long the force stretches over and how strongly it couples compared to gravity. All of this stuff up here is ruled out. So sure, there can be new forces down here, but look at what we're saying. We're saying that a force that stretches over about this far has to be 100,000th the strength of gravity, or less. And of course, you can go to shorter distances and the constraints become weak, but over every macroscopically relevant length scale, the size of a neuron in your brain, new forces have to be much weaker than gravity. And gravity is really weak. Here's gravity. The entire gravitational field of the Earth is trying its best to pull down the laser pointer, and I can hold it up. That's how weak gravity is. There's no way that a neuron has a gravitational field that is in any way relevant to what happens in the brain. And there's no way that a new force that is even weaker than gravity could be relevant to what happens in your brain. As far as our everyday lives are concerned, the laws of physics underlying them are completely known. People don't like it when I say this, so I'm going to apologize. I'm going to put the caveats on, things that I have not yet said, but people want to read into what I am saying here. Just because we know the fundamental laws doesn't mean we know the interesting laws. The overwhelming majority of working physicists, and every single person who is not a working physicist, is not spending their time thinking about fundamental physics, particle physics, gravity, that equation that I showed you before. They're thinking about atoms and materials and plasmas and fluids and all of the intricate, fascinating, crucially important, higher level, complex phenomena that actually run our everyday lives. You can get through your everyday life perfectly fine without even knowing about quarks and quantum field theory. I've seen people who have done it. I don't know why you'd want to be that way, but there are people who do it. And it certainly doesn't mean useful. The technological advance that is going to come from discovering the Higgs boson, there is no technological advance that is going to come from discovering the Higgs boson. The Higgs boson exists for about 1 zeptosecond. In technical terms, that's a really tiny period of time. We're not going to build better iPhones, cure cancer, or anything like that with the Higgs boson. It's not useful to know about the Higgs boson, but there it is. It's part of our theory. It's not a matter of deriving the higher level theories. If you want to understand how biology works, don't study particle physics. It's related, but it's not helpful because biology has its own domain of applicability. And we certainly don't understand all fundamental physics by any means. We don't understand quantum gravity, the center of the black holes, the Big Bang, dark matter, dark energy. The list goes on. I'm not claiming that physics is done. I'm claiming that we have a regime where we understand what happens. Okay. Nevertheless, now that I've given all you my apologia here, there are consequences. Knowing the fundamental laws of nature does have ramifications, implications for the higher level, the observable behavior of nature. So here's your equation that you know and love. This equation has implications, both very simple ones and much deeper ones. Here's an implication. Electric charge is conserved. You're not surprised to hear that. The total number of positive electric charges plus the total number of minus the total number of negative electric charges adds up to a number, and as long as the system is closed, that number never, ever, ever changes. That's an implication of this equation. But when you think about it, it's kind of an impressive implication. It means that even though this is spoken in the language of tiny little things, of the fundamental constituents of everyday reality, you can't build some big, complicated system that violates this. When you hear those people who have perpetual motion machines, it's not about, finding that they have somehow cheated in their perpetual motion building device. It's that they violate the fundamental laws of physics. There are more profound implications. Astrology is wrong. You probably knew that. But if you were to be asked, why do I know it's wrong, you would probably say, oh, it's bullshit, forget it, go away. But you would probably say, well, it's never been demonstrated, double blind, blah, 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 blah. Forget that. There's no force of nature that could make astrology work. The position of Saturn in the sky on the day you were born does have an influence on things here on Earth. It has a gravitational field and electromagnetic field. And it's much smaller than the gravitational field and the electromagnetic field of the nurse standing next to you when you were born. Could there be a new force that is not yet discovered by physicists that does astrology? No. There can't. We would have found it by now, and we haven't. There is no life after death. And I've heard very good atheists and humanists say, well, we don't know about this life after death thing yet because we don't have data. If you believe that quantum field theory is correct, and you want to believe in life after death, there has to be some way for the information about your immortal soul to be carried outside your body and to hold together in a coherent way and then land in some other organism at some other time. There's no way. There are no particles of which your soul could be made. There are no interactions that could carry that information away. We don't need to worry about this question. We know the answer. Knowing some of the fundamental rules by which nature behaves has implications for the larger picture. So let me talk a little bit about, and then I want to sort of undo all the good that I've just done. So there's a cartoon that is in the back of many people's minds. There's particle physics and gravity at the bottom, and then you have chemistry, biology, social sciences, etc. And I want to have my cake and eat it too. I want to say that yes, in principle, any biological organism or any collection of people can be thought of in terms of a set of vibrating quantum fields, that you're allowed to do that. And then if you know that equation I showed you and your calculational ability is really, really good, you can use Schrödinger's equation to tell me what happens next. In principle, you could do that. In practice, you would be nuts to do that. That is not the way to learn about biology, to learn about social sciences, or even chemistry. Even though, in principle, biological organisms are just collections of atoms, it's much, much, much more useful to think of them as biological organisms than to think of them as collections of atoms. If you meet somebody for the first time, if you're on a date, someone says, tell me about yourself. You do not start listing all the atoms in your body and their positions and their momentum. Except my students at Caltech sometimes do that. That's considered pretty hot, you know, if you're at Caltech. But most of us speak a language that is relevant at a higher level, a coarse-grained description of nature. So this is what almost all of science consists of. Not investigating just the fundamental quantum fields of nature, but investigating all of the emergent higher-level laws that tell us what this intricate hierarchy of possibilities is and how it works. Just as my favorite physics example, you can talk about a box of gas, the air in this room, in terms of atoms and molecules. If you want, you're allowed to do that. It just requires about 10 to the 30th equations, that's all. Or you can say there's a gas, it has a temperature, it has a pressure. There's of order 1 equations, there's a handful of equations you would need to describe it that way. You don't get everything exactly right. You're forgetting some information to do this, but you're forgetting things that are almost always completely irrelevant. So we are very, very fortunate to live in a hierarchical reality where there are ways to talk about the universe other than using the fundamental laws of physics. There are these vocabularies, these ontologies, these stories, these models, whatever you want to call them, that apply at the upper levels, and you don't even need to know how the lower level works. And what's interesting about this is that not only can you have different layers of description, but they can sound very, very different. Things that you thought were really important down here at the bottom level might not even show up at the upper level. I'll give you one very obvious example. My favorite example of what we call an emergent feature in a higher level theory, the arrow of time. The fact we already mentioned, the past is different from the future, right? The past is done, the future is up for grabs. I can make choices about the future. I remember yesterday, I don't remember tomorrow. Well, if you go back to Newton's equations, if you're Laplace or you're Schrödinger or whatever, that distinction between past and future is nowhere to be found. In the fundamental laws of physics, the future and past are on exactly equivalent grounds. There is no difference between the past and future as far as the fundamental laws of physics are concerned. Yet, you would be crazy to try to explain human behavior or biological evolution or even the evolution of cosmology in the whole universe without taking into account that in the macroscopic realm there's a very strong arrow of time. There's a very noticeable difference between the past and the future. So it's not true that just because something is invisible at the lower level, it can't be there at the higher level. They just need to be compatible. How do you make the arrow of time in the macroscopic world compatible with the reversibility of the microscopic world? It's because of the Big Bang. Because in the past, 13.8 billion years ago, the universe started in a very, very special, delicately arranged state. And it's like a little wind-up toy that was started there. It has been puttering along ever since, winding down, dispersing its energy as entropy goes up. We have a match. We have a way of mapping between the fundamental laws of physics and the macroscopic ones. It just requires knowing which macroscopic configurations are allowed. Then you find that words like cause and effect, memory, choice appear and are very important at the macroscopic level, even they're nowhere to be found at the lower level. So I would say, having gone through this whole journey, that teleology is absolutely acceptable in laws of science. It is on the table as a possibility. Teleology is the idea that the way to talk about a system is to say it has a goal. It is trying to find something. At the equation level of the fundamental laws of physics, there is no teleology. But that's not the end of the story. At the higher level, at the emergent level, at the macroscopic realm, there might very well be teleology. Remember, you agreed with me when I said the Roomba has a teleology. It was built in order to vacuum the room. There was a purpose. There was a reason why somebody built that Roomba. And that person who built the Roomba is made of atoms obeying the fundamental laws of physics. Is there purpose in the universe? Of course. I have purposes. You have purposes. You came here and you're just made of atoms. It's because you're describing yourself at a different level of complexity. So if teleological language, finding a purpose, moving toward a goal, is the best scientific theory applicable to a certain level, then there's every reason to talk that way. Here is some data. This is a picture of a cat chasing a mouse. How do we predict what's going to happen next when the cat is chasing the mouse? Well, you could figure out the location of every single atom and molecule in the cat and the mouse and the environment and then run Schrödinger's equation forward in time. And you would predict what would happen in the future. Or you can say the mouse is trying to escape, the cat's trying to catch the mouse. They have goals. That is a much more efficient, useful description of this higher level phenomena. All I'm trying to say is that that is perfectly okay. And we understand why these teleological actions can evolve. And the word evolve gives it away. It's this guy who told us how these descriptions can come of the mindless, purposeless interactions of ordinary atoms. Darwin, natural selection, explains the appearance of design even though there wasn't a designer. Emergent teleology. And it's actually, as a physicist, I want to say it's all because of the arrow of time, because the early universe was in a low entropy state. Again, that's another lecture that I'm not going to give. But the point is that Darwin explains how we can reconcile the appearance of purpose at the higher levels. Here is a picture of a peacock and a peahen. That peacock has a purpose. The peahen seems to be unimpressed by the peacock's purpose. This big fanned tail, there's a reason why there's this big colorful display going on. And Darwin explains how it evolved. So I think it's perfectly okay to contemplate higher level teleological vocabularies for explaining the macroscopic world. Now that's the easy part. Everything I've said right now, that's the simple stuff because it's science. We've been talking about how science explains the world and how the different layers fit together. The hard part is when you think about human beings, human life, questions like meaning, personal purpose, why am I here kind of stuff. Because now I disagree with a lot of my favorite thinkers in the sort of the atheist humanist community. I do not think that science is going to give unique, useful answers to these kinds of questions. Science is not going to tell us how to judge right from wrong. But the same kind of pattern applies. When we want to know what is moral, what is good, what is meaningful in life, what matters in Rebecca Goldstein's language, we're telling yet another story. We're constructing yet another model. The only difference is that the way that we evaluate whether a model works or not is not completed by fitting the data. You need to fit the data, but you're looking for something more as well. So I would argue that we should resist the temptation to think that science is all there is. There needs to be questions. There are questions that science is not going to provide a unique answer to. And, oh, fortunately I'm running out of time, so I can't tell you how to do that. But I can sketch out how it should be done. No, I mean, the point is, I don't have a favorite once-and-for-all answer to questions about what is right and wrong, what is purposeful and meaningful in life, why are we here, what goals should we have for ourselves. All I want is for them to be consistent with the laws of physics. And all I want is to point out that they're not determined by the laws of physics, even though they must be consistent. So where do you get theories? How do you evaluate stories that are fundamentally judgmental, fundamentally, what is it, prescriptive, not descriptive, fundamentally aesthetic? And the answer is, look at the real world. Look at what people actually do. Human beings are not blank slates. We are not computers that have not yet been turned on. We have desires, we have aspirations. Some of them come from biology, some of them come from culture, our individual life experiences. We have emotional reactions. There are things we want. There are things we think are good. The job of moral philosophy, or ethical theories, or aesthetic theories, and so forth, is not to dig down into some a priori stuff and derive rules for right and wrong that are absolutely airtight and logically impeccable. It's to take the messy reality in which we actually live, in which different human beings have different goals and different aspirations, in which individual human beings aren't even consistent with each other. They have things that they would say are right, and then they think about them more deeply and they realize that they're in conflict. The job of moral philosophy is to sort all that out, to figure out how we can individually go from our sort of inchoate, unsystematic judgments to a way of thinking that is systematic and sensible, and then to share those thoughts with other people and to come together as a community and determine how we should act in the world, what we should judge to be right and wrong. It's not universal, it's not objective, it's also not arbitrary. So the way that I like to think about this is that finding meaning in life is a creative act. It's not an act of discovery, ultimately. That equation I showed you for the laws of physics doesn't care. No right or wrong there, no meaning, no purpose. It doesn't say that something must be a certain way, or something is good, or something is bad. So as much as I love saying that the universe is made of atoms, I also love this quote by the poet Muriel Rukeyser, who says the universe is made of stories, not of atoms. And what she means by that, she's in no sense an anti-scientific poet. And she wrote a very long, beautiful biography of Josiah Willard Gibbs, the American chemist and physicist. And she's a big fan of science. But what she's saying is that once you go beyond the fundamental laws of physics, everything else, all of our other ways of talking, are stories that we tell that bring the universe to life. Sometimes those stories are purely instrumental. When we tell stories about biology or chemistry or social sciences, we're just trying to explain the data. We have a very utilitarian point in mind. When we tell stories about right and wrong, purpose and meaning, they're not purely instrumental. They are fundamentally aesthetic. They are fundamentally creative. And choosing which story to tell is the task that is in front of us in ways that are compatible with the fundamental laws of physics. And the final point I want to make is that even though this act is fundamentally subjective, is not determined by physical reality, it's also not arbitrary. That's another mistake you can make. So think of chess. Think of the rules of chess, right? Now the rules of chess are very, very specific. The pawns move in a certain way, the knights move in a certain way, etc. And you know what? We made them up. The laws of chess, the rules of chess, are nowhere to be found in the fundamental laws of physics. They're subjective. We invented them. But they're not arbitrary. You couldn't change the rules. You couldn't say that on Tuesdays the knights move diagonally and have just as good a game. There was a purpose in mind when we invented the rules of chess. We wanted to make a good game. We wanted to make something that was fair, something that was interesting, something that was intricate, something that would give pleasure and intellectual stimulation to generations of people, etc. We can't just go messing with the laws of chess. Not all possible laws of chess are equally good. And with morality, with meaning, with aesthetics, it's exactly the same thing. We make up notions of right and wrong, but it's not arbitrary. It's not that any possible notion of right and wrong is equally good. I got to put one substantive statement in here. So, for example, gay marriage. I would put forward the idea that there are different possible ways we could think about the morality of gay marriage, and you might reach different conclusions depending on your notion of the fundamental laws of physics. Fundamental laws of physics don't fix your conclusions, but they affect them. So one story that you might tell is that there is a natural way for human beings to be. God created Adam and Eve, not Adam and Steve. There's a natural form for human interactions to take, one man, one woman. That is a story you could tell. I would argue that story relies on some seriously flawed fundamental ontology. There's another story you could tell, that it says how to live is a decision that we human beings have to make, that is not given to us by God nor the universe. There's no naturally correct configuration. We get to decide how best to guarantee happiness, to protect human dignity, to live together individually and collectively in the world. Now, this point of view doesn't immediately and clearly tell you how to treat gay marriage, but it's kind of suggestive. It kind of says, you know what, we're all human beings. We should all learn to live together. We should let people be happy, and achieving those kinds of goals is how we should set up the society in which we live. So the bad news for Rick Warren is that he was wrong. It is all about you. God did not give you a purpose to living. That, in fact, the universe doesn't give you a purpose in living either, but that doesn't mean that there are no purposes to living. It does not mean that you cannot find meaning in your own personal life. It's that you have to create it. You have to create it in a way that is compatible with what we know about science, but there's more than one way to do that, and it's ultimately up to you what to do, as long as your reasoning is compatible with how the universe works. So I'd like to close by showing this image. It's a little bright in here, so you can't see it, but probably you've seen it before. This is the Hubble Ultra Deep Field. This is what you get if you take your camera and you point it at a blank spot of the sky, and you open the shutter and you leave it open. As long as your camera is attached to the Hubble Space Telescope, what you will see is that the sky is not blank, that it is full of galaxies. Within the observable universe, there are about 100 billion galaxies. Within our own Milky Way galaxy, there are about 100 billion stars, so roughly 10 to the 22 stars, just in the observable part of the universe. Every little blob here is a galaxy roughly the size of the Milky Way. So there are all sorts of, well, I guess they wouldn't call them humanist conferences, but there's, alienist conferences going on there, and they're looking pictures at us. And the point is that we human beings are really, really, really tiny. I know that some people are able to look at this picture and say, oh, the glory of God and creation, isn't that impressive? I can't imagine looking at this picture and thinking that the reason for this is so that I can be here. But what I can do is I can turn the camera around. This is the famous pale blue dot photograph that Carl Sagan had taken. This is the Voyager 1 spacecraft, 4 billion miles outside the Earth's orbit. They turned it around. They took a picture. That little speck, that one pixel, is us here on Earth, trying to drive home the fact that we are indeed very, very tiny. But despite the fact that we are tiny, we have turned the tables on the universe. We have lived for a very short period of time. We extend over a very tiny region of space. We're not that massive or complicated, really, and yet we can look at these pictures and we can understand them. We can capture all of this glory in our brains and contemplate it and think about ourselves and tell stories to ourselves about what it all means. And it's that creative act of discovering what is in the universe, making meaning and purpose for ourselves, that gives life its essential importance to us. Thank you. Thank you very much.
We have about 20 minutes for question and answer, so if you'll please line up at the microphones, and when it comes time, I'll let you know when the last question is.
I'm tempted to conclude that free will is a high-level emergent property of the underlying physical reality. Would you agree?
I would precisely agree. Minutes before I came up here, I removed the slide that I had saying free will is a high-level emergent property of physical reality. But yes, I think that's exactly the right way to think about it. So let me be a little bit more specific. In line with the ethos I suggested, I believe that as of right now, the best way we have of talking about human beings and human behavior is in terms of at least some ability to make rational choices between competing alternatives. And we would call that free will. And therefore, I would say that free will is part of our best high-level explanation. If someone else in the future is able to come up with a better high-level explanation, then free will would cease to be useful.
My name is Alrod Bell, and Sean, the conversation we had yesterday where I was challenging you in a way, I'm very happy to say I consider you not only a good guy, but an amazing speaker and teacher. For many years, for half a century, I have wondered about that paradox of light being both a particle and a wave, and in 1 minute, you explained it as a physiological artifact. Wow. Here's the issue that still remains. You describe the demon. Whose demon is it again?
Laplace's demon.
Laplace's demon. There are people still active in academia who are using that for what I see as the wrong ends that are very dangerous. I write about it, and it's there, and there's no time for me to talk about it. But it still is, I believe, an issue. But you are trying to eliminate that, and I thank you.
You're welcome.
Thank you for a superb talk.
Thanks.
I think you could summarize your conclusion by saying that morality should be intelligently designed.
Very happy to say that,
yes. One final correction to one of your slides. Herbert Spencer, not Hubert Spencer.
Oh, no. This is what I get for trying to be all interdisciplinary and crap. Yeah, all right. Thank you. Thank you. I will fix that.
Just a comment, about a year ago, wandering through a bookstore and concentrating on what I call the bumblebee books, you know, the black and yellow dummies books. I was shocked to find a book titled String Theory for Dummies.
Yes, I know the author. I'm making the acknowledgments of that book.
And if you go through it about 8 times like I have, something will stick.
It's the journey, it's not the destination.
Thanks so much for being here, and congratulations on making physics understandable to non-physicists. Question about climate change. Can you apply what you know about physics and all of the above, and what we might know about the future and climate?
If I were responsible, I would just say no. Fortunately, so, I mean, the climate is very, very complicated. I think the question that we should think about in terms of climate change is not a physics question. It's a Bayesian probability question. That is to say, I'm not an expert on climate. My knowledge of how electrons and gravity works is of absolutely no use in understanding how the climate works. I know how the greenhouse effect works, okay, but I also appreciate there's a lot more to the climate than just the greenhouse effect, so I wouldn't trust my own judgment. The reason why I say Bayesian probability is because the Reverend Thomas Bayes gave us a way of assigning the probability that a certain theory is correct in the presence of certain data, certain pieces of information. Now, I might a priori say, well, I don't know what's happening with the climate. Then someone shows me the graph of the temperature that goes like this, and someone shows me the other graph of the carbon dioxide that goes like this, and my meager physicist mind would go, you know what, I bet that putting carbon dioxide into the atmosphere is warming the Earth. And then I look at all of the climate scientists in the world, and they tell me that putting carbon dioxide in the atmosphere is warming the Earth. That's another piece of data, and it's overwhelmingly clear at this point in time with all of the information that we have, not because I'm a scientist, but because I'm a human being, that we human beings are making the Earth much, much warmer, and it is potentially very disastrous, and we should stop doing it.
You mentioned the Higgs boson, and it's sometimes referred to in the press as the God particle.
Yes.
I don't know what the Higgs boson does, but I know it's not God. And maybe you can explain why they call it that and how we can overcome it.
Well, so back in July, as I tweeted, you know, we're not allowed to call it the God particle anymore because now there's evidence that it exists. But look, the reason why it was called the God particle is because of marketing. That is the only reason. Leon Lederman, famous, great guy, Nobel Prize-winning experimental physicist, he was trying his best to drum up support for the American version of what the Large Hadron Collider is. This would have been the superconducting super collider that was going to be built in Waxahachie, Texas. He managed to convince the mayor of Waxahachie, Texas that this was a good idea, but public support was lukewarm at best. So he was trying his best to explain why the Higgs boson is important, and he dubbed it the God particle. And he claimed surprise when then people thought that the Higgs boson has something to do with God. It doesn't. It's just a really, really important particle. If the Higgs boson field were not there, then other elementary particles, electrons and quarks and so forth, would be massless. They would have zero mass. That means they would move at the speed of light. According to Einstein, if you have no mass, you move at the speed of light. Electrons are what form atoms. It's the electrons in the atoms that help the atoms join together to do chemistry in molecules. If the electrons are moving at the speed of light, they wouldn't fall into atoms. There wouldn't be any atoms, there wouldn't be any chemistry, there wouldn't be any molecules, there wouldn't be any life. So the Higgs boson, kind of a big deal, not actually God.
Yeah, thank you, Sean. It's a great talk. I think one of the reasons that I and a lot of other people find your talk so engaging is your commitment to engaging with philosophy from the scientific perspective, but also respecting that side of thought. So I was wondering just if there's any recommendations for a lay science and philosopher admirer, what kind of reading that you find particularly insightful in philosophy?
Yeah, that's a very, very good question. Yeah, I should do that. I should put up a blog post with the 10 best philosophy books for scientists. But off the top of my head, it's very hard. You know, some of my expertise in philosophy, such as it is very minor and is limited to the philosophy of physics, especially in those areas that it overlaps with my physics. There's no sharp line between doing philosophy and doing physics at this level. You're trying to figure out how the universe works. So there are books by people like David Albert, David Wallace, Hugh Price, Tim Maudlin, who are philosophers of physics, who are very well trained in physics, who know all the equations, and but they're much better at digging out the tiny logical inconsistencies that we physicists are so fond of introducing into our theories. So I would look at that level, at those kinds of names, for not people, there's many interesting things, but when you get into what's a good theory, how do you decide between theories, it becomes a bit of a mess. The more immediately productive areas of philosophy for me are where you're trying to figure out how does the universe work.
Thank you very much for a great speech. My name is Jim Colson, and I have a couple profound questions that bother me. Hope they don't bother you. I'm bothered by the Christian idea, and supposedly it's in the Bible, that this supposed God created heaven and earth. To me, that sounds like a singular heaven, where possibly so-called nice people go. And yet they're claiming that he's created the heavens, and I'm wondering how they can get this idea that and heaven and earth, we know where earth is, we don't know where heaven is, and yet they say, well, he created the heavens, which is not space, in my opinion. So I'm wondering if you know how they managed to make this leap of faith, or if there's some legitimate reason for it. My other question is they're burying a bunch of pure water tanks around Earth to catch something. What is it, and have they ever found it?
Yes, sorry. So the second question first. Not just water, but a whole bunch of things are being buried underground by physicists to explore, it went away, but to explore that diagram that I showed you of particles that are weakly interacting or very high mass. Dark matter, we think, fills the universe. Neutrinos fill the universe. They're very, very hard to detect. And it's hard up here on Earth to detect them because we have cosmic rays and all sorts of other noise. So we go underground, build very, very large detectors, wait for the very rare event where a dark matter particle bumps into something underground. For the first question about heaven, you shouldn't rely on me for theology advice, but I do, of all the reasons to be skeptical of the traditional religious narratives, the distinction between heaven and heavens is not high on my list of important things to worry about. However, there's a fascinating question of, if you took this kind of narrative at all seriously, what would heaven really be like? And I think that the story of heaven is a lot of people accept it because they're not really clear on the distinction between infinity and just very big. And you know, my wife Jennifer, who grew up in an evangelical Christian household, when she asked her mom what heaven would be like, she was told to be like going to church every day. And another atheist is born, right? There's a great book by Julian Barnes, History of the World in 10.5 chapters, where at the last chapter he explores what heaven might be like. And his conceit is, you get to do whatever you want, but we don't tell you what to want. So it's limited by your imagination, right? And so his sort of lower middle class Englishman goes to heaven, says, is my wife here? And he's, you know, do you want her to be here? And he's like, no. And he spends 1,000 years playing golf and having sex, and then he ceases his own life because he can't think of anything else to do. I think it's very, very hard to come up with a consistent idea of perfect, blissful happiness that lasts forever. I don't think that's how happiness works. I think there's a fundamental flaw in the very idea.
Hello, Sean. My name's Brian, and I just loved sort of how you're building purpose as something that you create, because I definitely believe that that it's a gift to be able to define your own purpose, to define your own way of life. But I wonder if you've experienced people who have maybe been afraid of creating their own purpose, and if so, if there's any sort of either consistent reason that you found for this, or any consistent thing that you could say to those people, as in for ways to sort of tell people, hey, it isn't so bad to be able to define what you want to do in life.
Yeah, so I mean, this is another good question, and I think there's two aspects here. One is that for those of us who are atheists and naturalists, we shouldn't claim that everything that we have learned in going from theism to atheism has improved the situation in terms of our personal well-being. I'm sad that there's no life after death. I think that the science tells me it's true. I'm kind of regretful that it's not true, and I'm happy to admit that. On the other hand, for the question of purpose and so forth, the analogy I like to use, it's a little infantilizing, so I apologize for that, but I say, look, there's a certain existential dread as an artist, a painter, when you're facing the blank canvas and anything could happen. You're on much safer ground if there are lines with numbers in there that tell you what to color in which places. But the great art does not come from coloring books. It comes from creativity. Two more questions, so you and you. Sorry. Yeah.
Okay, my question is, the information you've given to us today, how does it fit or not fit with Sam Harris's moral molecule?
Right. The information I've given you today directly contradicts Sam's way of thinking about the origin of morality. I'm just much less optimistic than he is. In fact, I'm determinately pessimistic that thinking about science is going to lead us to morality. If you read his book, I agree with 90-some% of what's in the book, because I certainly agree that understanding science is absolutely crucial to constructing a sensible moral theory. If we don't know how the brain works, if we are confused about whether or not there's an immortal soul that is embodied at conception and things like that, we're going to get morality all wrong. And so neuroscience and science in general are going to be very, very crucially helpful to choosing what is moral and what is not. But it won't be sufficient. And the simple argument I give is a scientific claim is a claim like the universe is expanding. And why is that a scientific claim? Because it could be wrong. Before you went out and looked, the universe might have been expanding, contracting, constant, whatever. It's an empirical question. All the possibilities are on the table. You go out and look and collect the data to find out what is right. That's science. Morality, is it moral to do this or that? I don't think that's something that you're going to do an experiment to figure out which option is right. I think that there is something beyond that.
Very good.
Though I'm a lawyer, not a physicist, I play one on TV because I do a fair amount of debates against religious philosophers like William Lane Craig, and they're very technical. I was wondering, Sean, if you would be willing to summarize your refutations of the first cause and fine-tuning arguments.
Sure. The first cause argument is much easier to refute because there's different versions of it. William Lane Craig has the Kalam cosmological argument that everything that has a beginning must have had a cause for that beginning. And the refutation goes as follows. Maybe it doesn't. How do you know? The refutation is you're not allowed to say that everything that comes into existence that has a beginning has a cause. Maybe it does. Maybe it doesn't. Both options are on the table. We're going to compare it to the data. Otherwise, you're just assuming what you're ultimately trying to prove. The fine-tuning argument is actually, that is far and away the most respectable argument for the existence of God. Why? Because it follows the rules. It's natural theology. It's looking at the world, looking at things that we observe, saying that they have a better theory, a better explanation for why certain aspects of the world are better. I think it's a failed explanation. I think that to the extent that God serves as an explanation for fine-tuning in the universe, that means that God is a theory that makes predictions. And the first prediction you would make is that you don't need 100 billion galaxies in the universe, you just need one. You don't even need all those other stars. You don't need a huge Big Bang with 10 to the 88th particles. Everything that God would have done, according to this logic, is very, very different from the universe in which we actually live. So it's good because it at least obeys the rules, but like any good falsifiable theory, like most falsifiable theories, I think it's pretty much been falsified.